There is a quiet misunderstanding hiding inside almost every conversation humanity has ever had about space travel. It appears innocent at first, simple, even logical. We look up at the stars, hear the phrase light year, and instinctively imagine an enormous cosmic road stretching endlessly through empty darkness. Then we ask the obvious question: how long would it take to cross it? But buried inside that question is an assumption so deeply rooted in human intuition that most people never stop to examine it carefully. We assume a light year is a fixed physical distance that demands a fixed amount of time to cross, no matter who you are or how you travel. It feels obvious. It feels natural. And according to the actual laws of the universe, it is completely wrong. To understand why, we first need to confront the scale of what a light year actually is. The phrase sounds manageable because our brains are used to hearing measurements every day: miles, kilometers, hours, years. But a light year is not just another large number. It represents the distance light itself travels through empty space in one full year while moving at the absolute speed limit of reality. That distance is approximately 5.9 trillion miles, not billion, trillion. Say it slowly and let the number settle into your mind. 5.9 trillion miles. The problem is that the human nervous system was never built to honestly visualize numbers at that scale. Evolution prepared us to understand forests, rivers, mountains, and short journeys across landscapes our ancestors could physically walk through. Once numbers climb into the trillions, the mind quietly cheats. It replaces the true scale with a smaller emotional substitute that feels easier to hold. So, instead of imagining reality, we imagine a symbolic version of reality. Let us try to feel the scale differently. Picture yourself standing at the edge of an unimaginably massive desert, not the kind of desert you see in photographs. This one stretches so far that no human being could ever cross it within a single lifetime on foot. Every day from birth until death could be spent walking forward, and you still would not reach the other side. The horizon never changes, the distance never seems to shrink, just endless heat and endless emptiness. Now, your intuition immediately tells you something about that desert. It tells you the desert itself is fixed, permanent. The only thing that changes is how quickly you move across it. Walk slowly, and it takes longer. Walk faster, and it takes less time. But the desert remains exactly the same size for everyone. That instinct is where the misunderstanding begins, because the universe does not actually behave that way at extreme speeds. Imagine stepping into a vehicle unlike anything humanity has ever built, a machine capable not only of accelerating faster and faster, but of doing something far stranger. As the craft gains speed, the desert itself begins to compress in front of you. The sand folds inward. The distance shrinks. The geometry of the landscape physically contracts along your direction of motion, like an accordion collapsing under pressure. The far side of the desert does not simply appear closer. It becomes closer. What once required an entire lifetime to cross now takes only minutes from your perspective inside the vehicle. And this is the critical point people often miss. You did not tunnel beneath the desert. You did not teleport around it. The actual measured distance between the two edges changed depending on how fast you were moving. That sounds like science fiction, but it is not fiction at all. It is one of the most thoroughly tested consequences of Einstein's theory of relativity. And this is where our current technology suddenly begins to look painfully primitive. Humanity's fastest spacecraft, including the Voyager probes, travel at roughly 38,000 miles per hour. That sounds incredibly fast until you compare it to cosmic distances. At that speed, crossing 1 light year would take nearly 19,000 years. Think carefully about that number. The pyramids of Egypt were built around 4,500 years ago. If we had launched Voyager before the invention of writing itself, it still would not have completed a 1 light-year journey today. Under the old Newtonian picture of physics, this creates a depressing conclusion. Space becomes a giant fixed prison of impossible distance. The stars remain permanently isolated because no biological civilization could survive the travel times required to reach them. But Newton's universe is incomplete. At ordinary speeds, Newtonian mechanics works beautifully. It predicts falling objects, planetary motion, and everyday engineering with incredible accuracy. But once velocity begins approaching the speed of light, the deeper structure of reality reveals itself. And the universe turns out to be far stranger than common sense ever imagined. In 1905, Albert Einstein introduced special relativity, and hidden inside its equations was a discovery that changed humanity's understanding of space and time forever. Einstein began with two deceptively simple ideas. First, the laws of physics are identical for all observers moving at constant velocity. Second, the speed of light remains constant for every observer regardless of motion. Those ideas sound harmless at first. Their consequences are revolutionary, because if the speed of light never changes, then something else must change instead. And according to Einstein's mathematics, what changes is space and time themselves. They are not separate things. They are woven together into a single, flexible structure called spacetime. And unlike the rigid universe imagined by Newton, spacetime can stretch, compress, and distort depending on motion. Distance itself is not fixed. Time itself is not universal. The faster you move, the more the geometry of reality transforms around you. The moment Einstein's equations revealed that space and time were connected, physics crossed a line that humanity has never fully emotionally recovered from. Because once space-time became flexible instead of fixed, one astonishing possibility emerged immediately. Distance itself could change depending on motion. Not as an illusion, not as a trick of perspective, but as a measurable physical reality experienced differently by different observers. This effect is called length contraction, and it is one of the strangest verified features of the universe. To understand it properly, imagine again that enormous desert stretching endlessly beyond the horizon. Under normal conditions, everyone standing still agrees on its size. 1,000 miles is 1,000 miles. But now imagine a traveler accelerating faster and faster across the landscape until their speed approaches the ultimate limit built into reality itself, the speed of light. At low speeds, nothing unusual happens. The desert remains stable. But as velocity climbs closer to light speed, the geometry of space-time begins responding in a way that feels almost impossible to accept intuitively. From the traveler's perspective inside the moving craft, the desert itself physically shortens along the direction of motion. The destination moves closer, not metaphorically, literally. And this effect follows a precise mathematical relationship known as the Lorentz factor. At everyday human speeds, the factor is so tiny that the contraction becomes invisible. Even our fastest aircraft and rockets move far too slowly for the effect to matter. But as velocity rises toward light speed, the contraction becomes dramatic. This is where interstellar travel transforms from hopeless fantasy into something far more complicated and fascinating. Imagine a spacecraft advanced enough to accelerate to 99.9% of the speed of light. From Earth's perspective, observers watching the journey would see the ship cross 1 light year of space in a little over 1 year. That part sounds straightforward. The ship is moving almost as fast as light itself, so naturally it covers nearly 1 light year per year. But now step inside the spacecraft. Look at the clocks on board. Watch the biological processes unfolding among the crew. Listen to their conversations. According to the equations of relativity, the people inside that ship would not experience 1 full year during the crossing. They would experience only about 16 days. 16 days to travel a distance Earth measures as 5.9 trillion miles. This is where many people instinctively resist the idea because it sounds like cheating. But nothing in relativity is being cheated. No physical laws are broken. The crew is not secretly moving faster than light. Instead, the geometry of space-time itself changes depending on the observer's motion. For the people on Earth, the distance remains 1 light year. For the crew moving near light speed, the distance contracts dramatically. Both measurements are correct within their own frame of reference. And if we push the velocity even higher, the consequences become astonishing. Suppose an advanced civilization builds a ship capable of reaching 99.999% of light speed. At that velocity, the Lorentz factor grows enormously. From Earth's frame, the journey still takes just over a year. But for the travelers aboard the vessel, only around 13 hours pass. 13 hours. less than a full day to cross what stationary observers consider one of the largest practical distances humans ever discuss. This is not science fiction mathematics invented to entertain audiences. It is experimentally verified physics built directly into the functioning of the universe itself. One of the clearest confirmations comes from subatomic particles called muons. These particles are created high in Earth's atmosphere when cosmic rays collide with atoms. Muons have extremely short lifetimes. Under ordinary conditions, they should decay long before reaching the ground. But they do reach the ground consistently. Why? Because the muons are moving near the speed of light. From our perspective on Earth, their internal clocks run slower due to time dilation. But from the muon's own frame of reference, something equally strange happens. The thickness of Earth's atmosphere contracts dramatically. Instead of traveling through dozens of miles of atmosphere, they experience a much shorter distance. The atmosphere itself becomes compressed, exactly as Einstein predicted. This experiment has been repeated and confirmed countless times across the world. Relativity is not a philosophical interpretation. It is measurable reality. And once you truly absorb this, the meaning of a light year changes completely. A light year is not a universal prison sentence forcing every traveler to spend the same amount of time reaching a destination. It is simply a measurement of distance from one specific frame of reference. Different observers moving at different velocities experience different geometries of spacetime. That realization changes the emotional relationship humanity has with the stars. For centuries, interstellar travel seemed permanently impossible because we imagined the galaxy as a rigid map of fixed distances. We assumed the stars were separated by walls of time. No biological civilization could survive crossing. But relativity quietly reveals a different truth. The universe rewards velocity. The faster you move, the more space-time itself compresses ahead of you. At sufficiently high speeds, the galaxy no longer behaves like an enormous frozen wilderness. It begins behaving like a traversable landscape. A civilization advanced enough to sustain near light speed acceleration could, in principle, cross distances that appear impossible to stationary observers. And this creates one of the strangest consequences in all of physics. From the traveler's perspective, reaching distant stars within a human lifetime becomes theoretically possible. But for everyone left behind on Earth, years, centuries, or even millennia may pass during the same journey. The travelers and the stationary observers do not share the same experience of time anymore. This is where relativity stops feeling like abstract mathematics and starts becoming emotionally unsettling. Because the deeper truth hidden inside Einstein's equations is not merely that space can contract. It is that reality itself is not experienced equally by all observers. There is no single universal clock governing the cosmos. No master timeline flowing identically everywhere. The moment people first hear about time dilation, most assume they misunderstood something. The idea feels too strange to fit comfortably inside ordinary human intuition. We are trained from childhood to think of time as universal. Seconds pass, minutes pass. Clocks tick forward together for everyone everywhere. Whether you are standing still, driving down a highway, or flying across an ocean, time appears steady and shared equally by all observers. But Einstein's universe does not work that way. In reality, time itself changes depending on motion. Not psychologically, not biologically, physically. And once you fully understand this, the entire concept of interstellar travel transforms from impossible fantasy into a deeply strange but mathematically consistent possibility. Imagine two identical twins. One remains on Earth while the other boards a spacecraft capable of accelerating to velocities extremely close to the speed of light. The traveler journeys across interstellar space for what feels like a relatively short period on board the vessel before eventually returning home. According to ordinary intuition, both twins should age at nearly the same rate. But relativity predicts something radically different. The traveling twin returns younger, not by metaphorical standards. Actually younger. Their biological processes, their heartbeat, their cellular aging, Every physical process inside the moving ship unfolds more slowly relative to the clocks and biology of the stationary twin on Earth. This effect is called time dilation, and it emerges naturally from the same relativistic structure that causes length contraction. The key insight is this: the speed of light must remain constant for all observers. That single rule forces spacetime to compensate in extraordinary ways. If distance can contract, then time must also stretch or compress depending on motion to preserve the consistency of physical laws. And unlike many strange ideas in theoretical physics, time dilation is not speculative. We measure it constantly. Modern GPS satellites orbiting Earth actually experience time at slightly different rates than clocks on the surface. Their motion and position within Earth's gravitational field alter the flow of time enough that engineers must continuously correct for relativistic effects. Without those corrections, GPS navigation systems would drift by miles every day. Relativity is not hidden in distant galaxies. It already shapes the technology people use every hour without noticing. Now, let us push this concept toward the stars. Suppose a spacecraft accelerates continuously until it reaches 99.999% of light speed. Inside the ship, the crew experiences time normally. Their conversations feel normal. Their meals, sleep cycles, and thoughts unfold naturally. Nothing about their biology feels distorted from their own perspective. But outside the vessel, the universe behaves differently. For stationary observers, time on board the ship appears dramatically slowed. And for the travelers themselves, external time races forward. This creates one of the most emotionally difficult consequences of relativistic travel. A crew could leave Earth, travel across dozens of light years within what feels like a manageable span of personal time, and return to discover centuries or even thousands of years passed back home. They would not merely travel through space. They would travel into Earth's future. That is the hidden price relativistic physics demands. The universe does not hand out shortcuts freely. It allows biological travelers to cross immense cosmic distances within their own lifetimes, but only by separating their experience of time from the civilizations they leave behind. And this changes the entire emotional meaning of interstellar exploration. Imagine astronauts departing for a nearby star system. Perhaps for them, the voyage lasts only a few years, but by the time they return, every person they knew is gone. Languages have evolved, nations have vanished. Entire civilizations may have risen and collapsed while the travelers aged only slightly. The galaxy becomes reachable, but home becomes unreachable. This is why relativistic travel feels simultaneously hopeful and tragic. Physics opens the door to the stars while quietly removing the possibility of returning to the same world you left. And yet, despite its emotional weight, the mathematics behind it remains stunningly precise. The equations governing time dilation arise directly from the Lorentz factor introduced earlier. As velocity approaches the speed of light, time aboard the moving ship slows relative to stationary observers. At ordinary speeds, the effect is too tiny to notice. But near light speed, it becomes overwhelming. At 99.9% of light speed, the Lorentz factor reaches around 22. That means time aboard the spacecraft passes roughly 22 times slower relative to Earth. 1 year for observers on Earth becomes only about 16 days for the travelers. Push closer still to the speed of light, and the effect intensifies dramatically. At sufficiently extreme velocities, entire human lifetimes on Earth could pass while only months unfold aboard the vessel. And this leads to a profound realization that most people never fully consider. The stars are not unreachable because space is too large. They are unreachable because energy requirements become enormous as velocity approaches light speed. Relativity does not forbid crossing interstellar distances within a lifetime. In principle, it permits it beautifully. The true obstacle is propulsion. As an object gains speed, accelerating it further requires increasingly vast amounts of energy. Near light speed, the energy demands become almost unimaginable. The closer a massive object moves toward the speed of light, the harder it becomes to push it faster. And according to our current understanding of physics, no object with mass can ever fully reach or exceed light speed itself. That ultimate limit remains intact. But the remarkable thing is that relativity does not need us to break the speed of light to transform interstellar travel completely. Near light speed motion alone is enough to compress distance and slow time so dramatically that the galaxy becomes, at least theoretically, navigable within a traveler's lifetime. This is the deeper lesson hidden inside Einstein's framework. The cosmos is not a rigid machine built from absolute distances and universal clocks. Reality is relational. Space and time reshape themselves depending on motion. Different observers inhabit different geometric experiences of the same universe. And once you see that clearly, the phrase "one light year away" never feels the same again. Because a light year is not a universal amount of experienced travel time. It is a measurement tied to a particular frame of reference. The universe does not impose a single shared reality on all travelers equally. Once relativity reveals that the stars are not completely locked behind impossible time barriers, a new question immediately takes its place. If near light speed travel can compress distance and slow time for the traveler, why have we not already begun moving toward the stars? Why are humans still confined to a tiny corner of the solar system, using rockets that would need tens of thousands of years to reach even the nearest stellar neighbors? The answer is both simple and brutally difficult: energy. The physics of relativity allows interstellar travel in principle, but the engineering demands become almost unimaginable as velocity approaches the speed of light. Humanity's current propulsion systems are not merely slightly insufficient. They belong to an entirely different technological era compared to what relativistic travel would require. Modern rockets operate by carrying chemical fuel and ejecting mass backward to create thrust. It is essentially a controlled explosion pushing a vehicle forward. This method works reasonably well for reaching orbit, landing on the moon, or sending robotic probes across the solar system. But on interstellar scales, chemical propulsion becomes painfully inadequate. Consider Voyager 1, the fastest spacecraft humanity has ever launched relative to the Sunday. It travels at roughly 38,000 miles per hour, impressive by Earth standards. Yet compared to light speed, it is almost motionless. Light moves at approximately 670 million miles per hour. Voyager is crawling through the cosmos at a tiny fraction of 1% of the speed needed for meaningful relativistic effects. At its current velocity, reaching the nearest star system, Alpha Centauri, would require around 70,000 years. Human civilization itself has not existed in recorded form for that long. This is the scale of the challenge. To experience the relativistic compression Einstein described, a spacecraft must accelerate to velocities incredibly close to light speed. And achieving those speeds requires staggering amounts of energy because as velocity increases, the energy required for further acceleration rises dramatically. The closer you approach light speed, the more resistant the universe becomes. Not through friction, not through air resistance, but through the structure of space-time itself. A useful way to imagine this is to picture pushing a heavy object across a floor. At first it moves easily, but now imagine that every extra bit of speed makes the object heavier and harder to push. That is roughly what relativity does to accelerating mass. The faster an object moves, the more energy it demands for additional acceleration. Near light speed, the required energy becomes enormous. This is why no massive object can actually reach the speed of light according to our current understanding of physics. Doing so would require infinite energy. But importantly, relativity does not require us to fully reach light speed for interstellar travel to become practical from the traveler's perspective. Even reaching 99% or 99.9% of light speed creates dramatic time dilation and length contraction effects. The challenge is building a propulsion system capable of sustaining that acceleration. And this is where human engineering enters territory that still feels partly theoretical. Scientists have proposed several concepts that might someday move civilization closer to relativistic travel. One possibility is nuclear fusion propulsion. Fusion powers the stars themselves by combining light atomic nuclei and releasing enormous amounts of energy. A fusion-powered spacecraft could theoretically achieve velocities far beyond chemical rockets while carrying significantly more efficient fuel. Another idea involves antimatter propulsion. When matter and antimatter meet, they annihilate each other completely, converting nearly all mass into energy. Even tiny amounts of antimatter contain staggering energy potential. In theory, antimatter engines could drive spacecraft to significant fractions of light speed. But there is a problem. Humanity currently produces antimatter in microscopic quantities at enormous cost. We do not yet possess the industrial capability to manufacture or safely store enough antimatter for practical spacecraft propulsion. And then there are even more radical concepts. Laser sail systems, for example, would avoid carrying fuel entirely. Instead, enormous lasers stationed near Earth could push lightweight spacecraft using concentrated beams of light. Projects like Breakthrough Starshot already explore early versions of this idea. Tiny probes accelerated by powerful lasers could potentially reach nearby stars within decades.